Have you ever wondered how a website can just instantly pull up your order from, like, millions of others? Or how your university just knows every single class you've ever taken? It really feels like magic, right? But underneath it all, databases are speaking a secret language. And it's a language of pure logic, a way of asking really precise questions to get really precise answers. Today, we're going to crack that code. So, here's our case file. This is the mystery we need to solve. How do you find the names of all university instructors who work in the Watson building? Now, it seems pretty simple on the surface, but the clues? They're locked away in different digital files. So we're going to act as data detectives, piecing it all together using the fundamental tools of a system called relational algebra. It's basically the blueprint for how databases think. And make no mistake, this isn't just some abstract academic exercise. This secret language, this underlying logic, is the engine that powers our entire digital world. From banking transactions to your social media feed, understanding this language, well, it means understanding how all of this stuff actually works. Okay, let's get into it. Our case file is this university database. You can think of it as a set of digital filing cabinets, and each one holds a different kind of information. This diagram here, this is our map of all the clues. Each one of these boxes, instructor, department, that's a separate file, or what we formally call a relation. Now, here's the catch. The instructor file has the professor's name, sure, and the department they work in, but not the building. The department file has the building, but not the instructor's name. The answer we need is in there. We just have to figure out how to connect the dots. To solve this, we're going to need a toolkit. And our first two tools are for investigating just a single file at a time. I like to think of them as the filter and the slicer. Our first tool is the select operator, which you'll see represented by the Greek letter sigma. Just think of it as a super powerful filter, kind of like a magnifying glass. You give it a condition, any condition, and it keeps only the rows from your file that match that condition. Everything else just gets tossed aside. It lets us focus only on the clues that actually matter. So, for example, if we apply a filter for physics on our full list of instructors, boom, just like that, our list is instantly narrowed down to just the 2 instructors who work in the physics department. Everyone else, filtered out. It's our very first step in zeroing in on the answer. Now for our second tool, the project operator, represented by the Greek letter pi. So if select acts like a horizontal filter for rows, you can think of project as a vertical slicer for columns. It lets you get rid of any columns of information you don't need, keeping only the specific ones you actually care about. For instance, if we project the instructor table and say we only want the ID, name, and salary, well, this is what we get, a nice, clean, focused list. That whole department column is just sliced away. It's hidden from you because we told the database we don't need it right now. Okay, so filtering and slicing one file at a time is pretty useful, for sure, but the real detective work, that begins when we start combining clues from different files. This is where the magic really starts to happen. And that brings us right to the heart of our mystery. We've got the instructor's name in one table, and we've got the department's building in a completely different one. The clues are scattered all over the place. So how do we build a bridge between them? The answer is our master tool, the join operation. A join is really smart. It looks at 2 different tables, and it merges rows from each one based on a common piece of information. So for us, it's going to use the dept_name column, which exists in both tables, to perfectly match an instructor to their correct department. And will you look at that? We now have one single combined view. Every instructor's name is sitting right next to their department's building and budget. That join operation just connected the clues from our 2 separate files into one single coherent story. All right, we have all our tools now. The real power isn't just using them one at a time, but chaining them together, one after another, to build a query that can crack even a complex question. So let's solve this thing. Step 1. We take our filter tool, that select operator, and we point it at the department table. We tell it find only the departments where the building is Watson. And that gives us a very short list, just physics and biology. Step 2. Now we take that small result we just got from step 1, our list of Watson building departments, and we use our join tool. We combine it with the full instructor table, matching on the department name. So now what we have is a list of only the instructors who work in those specific departments. And for the final move, step 3, We take that combined list and we bring in our slicer tool, the project operator. We tell it to just throw away all the other information and give us just the name column. And there it is, our answer. The instructors in the Watson building are Einstein and Gold. Case closed. We solved it by composing 3 simple operations, filter, join, and slice, into one single, powerful expression. Now, I know this might all seem a little academic, but this algebra is the fundamental logic engine that makes the databases we use every single day so incredibly powerful and fast. And there's a really key distinction here that we need to understand. You see, on one side, we have relational algebra. It's procedural. It's a step-by-step recipe that tells the database exactly how to get the answer. On the other side, we have SQL, which is the language most people actually use. SQL is what we call declarative. You just tell the database what you want, not how to get it. It's like ordering the dish at a restaurant. You don't go in the kitchen and write the recipe. So what's the connection? Well, when you write a really simple request in SQL, the what, the database has this brilliant internal component called a query optimizer, and its job is to be a master translator and a master strategist. It takes your simple request, and then it figures out the absolute best possible how, the most efficient sequence of these relational algebra steps to get you your answer as fast as humanly possible. It might decide to filter first and then join, or maybe join then filter, whatever minimizes the work. That is its secret weapon.
And hey, don't just take my word for it. As the source text puts it, the optimizer finds an efficient way to compute the result, rather than just blindly following the steps you might have implied. This automatic optimization is what makes modern databases so mind-bogglingly fast.
And that brings us to a final, much bigger thought. We just acted like data detectives, laying out every explicit step to solve our case. But we also learned that the database has its own internal detective, the optimizer, that can figure out the best steps all on its own. So if we can just tell our tools what we want, and they're smart enough to figure out the how, what other kinds of complex problems could we solve that way?